Hi guys, welcome to lecture 4-10. In this video, we will start chapter 13, and we will cover chapter 13 over the course of 2 lectures. So in this first lecture, we will go through the properties of acids and bases. We will learn about some of the chemical definitions, like what chemically is happening when something behaves like an acid or a base. And that will lead us to learning about some of the reactions of acids and bases. And then the next video, we will go through things like the pH scale and the mathematics of acids and bases. That will give us a good insight into what this acid-base concept means. And that's a good place for us to get started. So let's talk about first the properties of acids and bases. So when we first started this course, we talked about what does it mean to study chemistry? What is chemistry? And we determined that chemistry is fundamentally the study of matter, all the stuff that exists as matter, and the changes that it undergoes, the chemical reactions, the transformations that it undergoes. Now, the acid-base system is a very big part of that because it is a way that we can take a set of properties that we see or observe on a substance and say, well, all of these properties on the substance say that we should be able to call this an acid of some kind or a base of some kind. And if we can say that, then we are able to predict the ways in which it will react and extrapolate what we already know about other acids and bases to this new compound. And that's really what acid and base chemistry is all about. So let's go back to the beginning and think, what are things that we can observe about a chemical substance, its properties, that would enable us to classify it as either an acid or base and put it into one of these 2 buckets. So let's get started with that. What are the properties, the first things you can think of when you think of an acid or a base? Well, for me, one of the first things I think of when I think of acids is their sour taste. And for bases, it turns out, have a almost exact opposite taste. They have a bitter taste. And you might be thinking to yourself at this point, well, how are we going to go around and taste all of these chemical substances? That sounds a little bit dangerous. And yeah, it definitely is, perhaps foolhardily. Now, if you look actually at chemical reference materials, up until recently, things like you'll look in something called the Merck Index, and you'll look in substances that you'll find very, very commonly you'll see a taste listed. So you'll look up some chemical compound that you know is toxic, like it's from like some poison dart frog, and it'll say isolated as shiny white needle-like crystals, taste bitter. And this is something that you'll see. And often they would classify compounds based on their taste. So they would call them alkaloids, which means bitter tasting. And of course, we have new methods available to us that allow us to go beyond taste and also not risk tasting something. But it's interesting to note that up until very recently, that was a major part of the chemical analysis, was taste, smell, and touching something, that sort of thing. So bitter taste, that would be for bases. Texture is another important property for both acids and bases. Many acids have a rough or gritty-like texture, whereas bases feel almost slippery, like soap. So for most people, this is as far as acids and bases really go, just to those basic sensory observations. But for early chemists studying the substances around them, they would collect other observations. So they would take a bunch of these things that they were calling acids based on their sour taste or their gritty texture, and then performing other experiments with them. And that's what we want to talk about next, or what are some of the chemical observations that can be made. So for example, if you take these things that are sour and gritty, these things that are acids, and you treat them with a metal, you will see something. You've seen this before, actually, in our lab, is that acids react with metals frequently to produce gases. So you'll see bubbles going out of it. And it turns out that flammable gas is hydrogen. So that's definitely one observation that we see with acids, is that they will corrode metals and as a result produce H2 gas. Now, bases don't do this. If we put a base into the same metal, these things that taste differently and are slippery, they don't react to produce gases. They, in fact, they do other things though that acids don't do as much. For example, bases will react with things like pigments or dyes and change their color. So that's something that we see with bases quite a bit. Organic materials like organic dyes change their color when they react with bases, but they don't with acids. Some other chemical behaviors we see with acids include that acids react with bases. So if you take these two things and you put them together, they end up doing something that we call a neutralization. And so it's like you take an acid and you take a base, a sour and a bitter thing, and you put them together and they no longer are sour or bitter. They're something else completely. It turns out that they're salts. So if you take an acid and a base and you react them, they form a salt. So acids react with bases and bases react with acids to produce salts. Another chemical thing that we see with acids is that acids react with minerals. So you can take something like limestone, which is calcium carbonate, and you can put it into an acid and it will produce carbon dioxide gas, more of this bubbling. Now bases don't do that, but bases do something else. They react with fats and oils, so like animal fats, vegetable oils, and as a result, you produce a soap, a very unique substance that is very important in terms of human culture and human industry, it turns out. So bases do this thing called saponification. It's very interesting. So those are some properties of acids and bases. Now, we're going to fast forward a little bit in time and get to the place where chemists first started actually describing what the chemical properties were. Instead of these just qualitative observations, let's get down to what's actually happening at the molecular level. And we're going to talk about the definitions of acids and bases. So if we go back in time to around the 1850s, early 1900s, we start to see chemistry really emerging into its own as a rigorous science from sort of a background of previously more of a sort of a mystical relationship with matter being alchemy. And some of the first major figures in this scientific development of chemistry is, one of them is Svante Arrhenius, who is definitely legendary in the field of chemistry. We're going to talk about his definition of acids and bases, which he put forth to describe what an acid is at a molecular level. So what Arrhenius said, and what we say is the Arrhenius definition for an acid, or an Arrhenius acid, is a substance that generates hydronium ion in water. And hydronium he defined as water with an extra H plus on it. So it would have the formula H3O with a plus charge, and he called that hydronium. So an acid, under the Arrhenius definition, is a substance that generates this hydronium ion. And furthermore, the more acid that you would put in water, the higher the concentration of this hydronium ion. Let's look at an example of an acid doing this in solution. Let's look at hydrochloric acid, for example. Hydrochloric acid is HCl, and hydrochloric acid is a gas. And in Arrhenius' time, they had access to this hydrochloric acid gas. Now, if you take this gas and you bubble it into water, the water, before you bubble it in, is completely normal. It's room temperature. And as you bubble this hydrochloric acid in, it changes quite dramatically very quickly. It suddenly starts to take on, if you get at it in a quick enough time and taste it before it gets too acidic, it definitely starts to taste sour. It starts to smell like an acid, and it will start to be very corrosive towards metals. It also gains mass as you do this. And what Arrhenius said is that this HCl is reacting with water to produce hydronium, or H3O+, and chloride ion. Now, for a complete acid-base theory, you can't just come up with a theory of an acid and walk away. You need to do something else as well. You need to come up with a theory for what a base is. And then additionally, on top of that, the theory needs to have another layer that we will see here in a minute. For now, though, let's look at what Arrhenius put forth as his definition of a base. Arrhenius said that a base must be a substance that, when put into water, that substance generates hydroxide. So Arrhenius' definition was that a base is a substance that generates hydroxide, or OH minus, in water. So here's an example of an Arrhenius base. Let's use sodium hydroxide. So sodium hydroxide is a solid salt, and when we dissolve it in water, it dissolves readily. As it dissolves, the water gets very hot. So this is an exothermic process. And what Arrhenius thought is that the sodium hydroxide, when it's dissolved in water, ionizes and forms sodium cations, but more importantly, for being a base, it also generates hydroxide anions. And that qualifies it as being an Arrhenius base. So Arrhenius has now a theory of what an acid is and what a base is, but beyond that, a good theory of acids and bases needs to, at a minimum, be able to explain at least the fact that an acid and a base must be able to react together to somehow destroy one another or to neutralize one another. Because this is an observation that's been made. You can take an acid and put it into water and it's acidic. You can take a base and put it into water and it's basic. But then you put those two things together in the right amount and suddenly it's not acidic or basic at all. It's neutral. It's almost like regular water again, maybe with the addition of a salt, but that salt can be removed and then you have pure water back. So essentially you destroy the acid and a base together. And Arrhenius' theory quite elegantly solves this problem, or puts forth an idea of what happens when an acid and a base react. And it's based on the fact that an acid produces hydronium, but a base produces hydroxide. Furthermore, a hydronium can react with a hydroxide to produce, guess what? Water in this chemical reaction, where we have one hydronium, one hydroxide, and from that, we can produce two water molecules. This is called acid-base neutralization, and it gets us a very good understanding of what's happening at an aqueous level. And while the Arrhenius definition of acids and bases is quote-unquote older, I don't really actually like that phrase. It implies that it's somehow less valid, and actually it's not less valid. This is, in water, this is what we believe is happening with many types of acids and bases. So what we're going to do now is learn more modern theories, but they merely, I would say, just add to the Bronsted acid definition. It's not that they exclude it. All of this is actually encompassing the entire theory of acids and bases. So we don't want to say that the Bronsted theory is better. It's just a little more general. It's slightly different. So let's look at that. Let's look at next another theory, which is called the Bronsted-Lowry definition of an acid and a base. Now, if we fast forward a little bit to the year 1923, we see that there was a new theory put forth for acids and bases, not to replace the Arrhenius definition, but to add on to it. And this theory of acids and bases was put forth by two chemists working independently of one another, one in Britain and one that was Danish. And these guys, Bronsted and Lowry, defined acids and bases in terms of the exchange of something that we call a proton. A proton, we should define real quick. I might have used this term before. A proton is, of course, it's a subatomic particle, but we often refer to the atom H, hydrogen, with a plus charge as a proton. Now that's because a regular neutral hydrogen atom consists of one subatomic proton and one electron as a system. Now, if we remove the electron from a hydrogen atom, we are left with a positively charged hydrogen atom because it consists only of a proton. So it makes sense for us to call an H plus a proton. Now, the Bronsted-Lowry definition relies upon this idea of the exchange of protons, because what it says is that an acid is a proton donor, something that gives up a proton. And a base happens to be a proton acceptor, something that can receive a proton. Now, it might take you a few examples to work through before you completely absorb that information and to really understand it from a deeper level. One analogy that I like to just put forward kind of up front that might help you remember it as we go through the different examples is a sort of pitcher-catcher analogy. So we can imagine this proton, this H plus, as being sort of like a baseball. And there are two characters sort of throwing this baseball back and forth. And we can think of the acid as sort of, at least initially, the one with the H plus and throwing it to the base where the base catches it. And this is the pitcher-catcher analogy. Now, one thing that I like a lot about this analogy is that it highlights a very important aspect of the Bronsted-Lowry definition of acids and bases, namely that proton exchange can happen in both directions. So the base originally on the left that caught that proton can throw it back. That makes it act as a quote-unquote new acid, which we'll learn to call a conjugate acid. And likewise, the new base we will learn to call the conjugate base. So the roles reverse depending on who has the proton, the acid or the base, and they exchange it back and forth. And that's a very important aspect of acid-base chemistry, that the Bronsted-Lowry definition really is what really makes it as important as it is. So what we're going to do on the next page is learn about this concept of conjugate acid, conjugate base, and apply it to some examples. So let's look at an acid-base reaction in the context of this Bronsted-Lowry acid-base definition. So I've drawn hydrochloric acid and ammonia, and I will define the hydrochloric acid as the acid and ammonia as the base. And what we want to do is predict, based on this Bronsted-Lowry idea of a proton exchange happening, being the acid is the proton donor and the base is the proton acceptor, let's draw the products of this acid-base reaction. So if the acid donates a proton, that means hydrochloric acid will lose its H+. And what would be left behind is a chloride anion. Why chloride? Well, because the hydrogen is left. Why anion? Well, because if we're losing a plus charge from a neutral molecule, we go from 0 to we have to subtract a +1 from 0, so that's a negative. So we get a minus charge. And then where does that proton go? Well, it has to go to that NH3, that ammonia. So we would have 4 hydrogens on ammonia instead of 3, and that's called ammonium. And that would have a positive charge because we're adding a plus charge to a neutral charge. So in the end, we will have chloride and ammonium. And that happens to be a salt. It's called ammonium chloride. So let's take a look at what the Bronsted-Lowry has allowed us to do. It has allowed us to explain what would happen outside of water. So there's no water involved here between something that we call an acid and something that we call a base. If we know that this thing is an acid and it can donate its H+, and we know this other thing is a base and can accept it, it predicts the molecular species, the ions, that would result from this. It also takes into account or explains neutralization, that you can take something that has this proton on it, that's the acid, but to neutralize it means to transfer it somewhere else. And we get a salt as a result, 2 ions together. So it explains that as well. Let's take a look at another example of a Bronsted-Lowry acid-base reaction. This time we will look at hydrochloric acid reacting with water, which you might remember we looked at in the context of the Arrhenius definition. So let's see if we can explain the same reaction that Arrhenius does, but using Bronsted-Lowry definition of acids and bases. So dissolving hydrochloric acid in water results in the production of hydronium ion and chloride anion. So based on this result, what can we say is acting as the acid? Well, if we take a look at what's accepting a proton, it's water. Water goes from H2O to H3O+. So that would mean water is acting as the base. And that should mean that hydrochloric acid is acting as the acid. To do so, it must be donating a proton. And if we look at it, HCl becomes Cl-. And so that means it must have donated a proton. So we see there's an acid, which is HCl, and we have the base, which is H2O. So let's just answer these two questions. What is the proton donor? The proton donor would be HCl, or the acid. What is the proton acceptor? That would be H2O, or the base. So as I mentioned on the previous page, a really important aspect of the Bronsted-Lowry definition of acids and bases is this concept of reversibility, that an acid-base reaction can be thought of as a forward-going reaction, where we have the acid and the base on the left, but then we produce, by exchange of a proton, an opposite pair on the right. So it's like there's a new acid and a new base because there's a new sort of pitcher and a new catcher, or new proton donor and a new proton acceptor. So we call this exchange of protons, we call the products of this exchange of protons the conjugate acid-base pairs. So we'll kind of read through this. Because acid-base reactions can occur in both the forward and reverse direction, we use the labels acid plus base and conjugate acid plus conjugate base to differentiate between each side of the reaction equation. So as you can see here, I'm drawing sort of an overview of this idea using a generic acid, which we're calling HA on the left, and a generic base called B on the left. Now, when these two undergo a reaction, the proton that I put in red there on the acid is exchanged. It's donated to B. And that's in the forward direction. That's why we call B the conjugate acid, because we can imagine now HB is the one that can donate the proton over to the A minus. And that's why A minus is called the conjugate base, because it can accept the proton. And they just can go back and forth like this, constantly changing roles, where they're called, one is called acid, one is called base. And then on the right-hand side, there's the conjugate ones, conjugate base and conjugate acids. And the roles are reversed. The acid always becomes the conjugate base, and the base always becomes the conjugate acid. So now what we're going to do is work through some examples where I'm going to write the formula of some acids here in this table. And from that formula of the acid, I want to show you how to write the formula of the conjugate base. An acid always turns into a conjugate base. So we're going to learn what the process is for writing that formula out. Because I need this space right here, I'm going to erase this diagram. So if you need it, please pause here so you can write down that information. So when we want to write the formula of a conjugate base, which we'll have to do when we want to write the product of an acid-base reaction, what we do is we write the formula, the same acid formula, but we deduct a proton from it. So we subtract that, we take it off. And correspondingly, we have to reduce the charge by 1 because we're losing a positive charge. So let's try that with a few different acids. So for example, hydrochloric acid, or HCl. We've done this already. To write the conjugate base, we take a proton off. That leaves Cl behind, and we reduce the charge by 1. So instead of being neutral, it's -1. So chloride is the conjugate base of the acid HCl. Let's try another one, sulfuric acid. Sulfuric acid has the formula H2SO4. So if we want to write the conjugate base of sulfuric acid, we have to remove 1 proton. So we write the formula with 1 less of those hydrogen atoms. So instead of 2, there would be only 1. So it would be HSO4. Now the charge goes from neutral to -1 because we reduce by 1. So this is called hydrogen sulfate, and it has a formula HSO4 with a -1 charge. Now really anything that has a proton could theoretically donate that proton. So if you can donate a proton, you could be an acid. So let's see, what would the conjugate base of HSO4 -1 be? What would the conjugate base of hydrogen sulfate be? Well, we would have to do the same process. We would have to remove that remaining H, that remaining hydrogen atom, and we'd be left with just sulfate, or SO4. What would the charge be? Well, we have to subtract 1 from -1. That would give us -2. So the conjugate base of hydrogen sulfate is sulfate with a 2 negative charge. So now let's talk about how we would write the formula for a conjugate acid. For a conjugate acid, we take the formula of the base, but instead of subtracting a proton, we add a proton to it. That's because bases accept protons. So we write the formula of the base with one additional proton, and then we increase the charge, because we're adding an H plus to it, by 1. So for example, what if we had the base hydroxide? Well, we would have to write the formula of hydroxide, but with an additional hydrogen. So instead of 1, we would have 2 hydrogen atoms, and the charge would be neutral. So the conjugate acid of hydroxide is water. What's the conjugate acid of water? Well, that would be H3O plus, or hydronium. Let's try another one. How about nitrate, NO3 minus? Well, we would have to add a hydrogen to that, so the conjugate acid would be HNO3 with a neutral charge, or nitric acid. So that's how we write the formulas of conjugate bases and conjugate acids. Now, what we're going to learn next is how this can help us predict reactions between acids and bases without knowing a lot more than just this theory and this concept of conjugate acids and conjugate bases. So let's go to the next page. So what we're going to do first on this page is I'm going to write out some acid-base reactions, and what I want you to do is go through, look at them, and label each one, each species in the reaction, find the acid and the base, and the conjugate acid and the conjugate base, and just like write under it like acid base, conjugate base. So here we go. So in this first example, we're looking for the acid and the base on the left-hand side. So to do that, we look at each component, each species, so water, and then we have hydrogen sulfide, and we're seeing which one has lost a proton. So we look at the other side. So if we look at water, it turns into H3O plus. Well, that's gaining a proton, so that's not what an acid does. If we look at H2S, H2S looks like it's lost a proton because it goes to HS minus. So that would be our acid, H2S. So now we need to confirm that water is acting as a base. So we look at water on the left, and we see it's H2O. On the right, it becomes H3O plus. So that means going from the left to the right, it has gained a proton, or accepted a proton. That means it's acting as a base. Now to find the conjugate pairs, what we have to do is imagine going in reverse. So from the right to the left. And deciding at that point, determining what is donating or accepting a proton going from the products to the starting materials. So let's take a look at what, say, hydronium is doing. If we start at hydronium and we go to water, what does it have to do? Hydronium, to turn into water, means hydronium needs to donate a proton. That means hydronium would need to act as a conjugate acid to do that. So hydronium is a conjugate acid. What about HS minus? Well, if HS minus turns into H2S, that means it needs to accept a proton. And that means it must act as a conjugate base. Let's look at another example. So the first thing we should do is find the proton donor, or acid, on the left. We notice that the species that gives up a proton is the acetic acid, because it goes from acetic acid to acetate on the right. So that would be our acid. And our base is the proton acceptor. That would be cyanide, because it goes from Cn minus to HCN. Then we look at the other side and we want to find the conjugate pairs. So hydrogen cyanide, to turn into cyanide, must donate a proton. So that would be our conjugate acid. And acetate, to turn into vinegar, or acetic acid, I should say, has to accept a proton. So that would be our conjugate base. All right, let's try one more. So here we can see the proton exchange starting from ammonia, which is donating a proton, so that would be our acid, to this what's called a tert-butyl lithium. This is an organic base, one of the strongest bases known. This would be our base because it's accepting the proton. And then on the right, if we consider these things going reverse, this NH2 minus, that's called lithium amide, that would be our conjugate base, and the proton donor would be this tert butane, which would be our conjugate acid. Now, just a few tips as we go through learning about these acids and bases as we continue. The first tip I would say is when you're doing acid-base reactions, only worry about exchanging one proton at a time. There are situations where you might have more than one, but don't worry about that in the beginning. Just do one at a time. The second tip is really anything with a proton can act as an acid. So H2O or HNO3, we really can include anything with one of those hydrogen atoms attached to it. And the third tip is that many molecules can act as both acids or as bases, depending on the situation. We call this behavior amphoterism, and a good example of this would be water. Water can do things like donate a proton, so it can act as an acid by giving up one of those hydrogen atoms. It can also accept a proton, so it can act as a base, and that would generate hydronium ion. So this behavior we call amphoterism, where a molecule can act as an acid or a base depending on the environment that it's in. Lots of molecules have this ability. So now that we've had a little bit of experience with these acid and base reactions, let's try writing out some reactions based on what we know. And in these little practice problems, what I'm doing is I'm giving you what's acting as an acid and what's acting as a base, and you need to just figure out what the products are. So let's go through each one of these. So we're told that dihydrogen phosphate is going to act as the acid and hydroxide is going to act as the base. So let's write those out and write down acid under the hydrogen phosphate and base under the hydroxide. Now we need to predict the products. So what we're going to do is exchange one proton. So we're going to transfer a proton from the acid to the base. So the conjugate of dihydrogen phosphate would be hydrogen phosphate, and that is our conjugate base. And the conjugate acid, that would be the conjugate of hydroxide, is water because it gained a proton. And the charge of that, of course, is 0. Let's try another example. Iodide acting as a base with water, thus acting as the acid. So the proton is donated from water to iodine, and we get HI and hydroxide. The HI is the conjugate acid, and the hydroxide is the conjugate base. Okay, so let's try one more. Hydronium acting as an acid, with acetate acting as the base. So the proton exchange starts from the acid, which is hydronium, and that proton needs to go to the base, which is acetate. So the products of this reaction would be water and acetic acid. Water is the conjugate base, and acetic acid is the conjugate acid. So we've covered a lot of ground already about acids and bases, and we don't really have that much further to go in this chapter. I want to end with this table today, which describes the 6 quote-unquote strong acids. Now we're going to be learning about the difference between strong and weak acids and what that means. But what I want you to start with first is understanding that there are a limited number of what we call strong acids. There are 6 of them. And the rest are weak acids. So I want you to know 2 things. I want you to know what are the 6 strong acids, what are their names, and what are their formulas. So let's list those out. The first 3 strong acids are really easy to remember. They're also known as the binary acids. That's because they contain 2 atoms. One is a hydrogen atom, and the other is one of 3 different halogen atoms. We have HCl, HBr, and HI. These are called hydrochloric acid, hydrobromic acid, and hydroiodic acid. Notice that the halogen missing is fluorine. Hydrogen fluoride is an acid. However, it's a weak acid. These are the three binary strong acids, HCl, HBr, and HI. In addition to these three binary acids, there are an additional three strong acids which contain oxygen and another atom. The first of these is nitric acid, or HNO3. That's nitric acid. We also have sulfuric acid, or H2SO4. That's sulfuric acid. Finally, we have perchloric acid, which is HClO3, perchloric acid. So next time what we will start with is what makes these acids strong and the others weak? What defines a strong acid or a weak acid? And then we will go into learning more about the quantitative aspects of acids and bases. So we'll start with the pH scale, and then we will look at what actually is pH, and we will learn how to calculate concentration of things with acids, so concentration of hydronium, concentration of hydroxide, using what we know about acid-base chemistry and some numerical techniques. So with that, I will end this lecture. I hope you're doing well. Please let me know if you have any questions.